We are resuming after a while our quantum information and coherence talk. For those who are coming for the first time, this is a very basic tutorial level talk that we have been doing for the last few years, and that in the broad area of quantum information and coherence. And today we have Mr. Mishkat Bhattacharya. Mishkat has been a pretty regular visitor to IIT Kanpur, also
pre-COVID.
Pre-COVID, yeah, pre-COVID. Yeah, so
he's our Ganesha. He's our Ganesha.
Actually,
he starts the QuiC Talk.
So yeah, every academic session, he's the one that kind of.
He's saying I have a big nose. That's what he's saying.
So yeah, last 2 years he could visit again because of the same COVID. Everybody knows. So he's back again this year, and so most of us already know him pretty well. For those who do not as much, Mishkat has his bachelor's in engineering physics from IIT Bombay, and then he went to University of Rochester where he finished his PhD in the broad area of actually experimental quantum optics, just to make it so that I don't forget, experimental quantum optics. After that he decided he wants to do theory, and then he did several postdocs and then joined RIT, Rochester Institute of Technology, in 2011. And now he is a full professor there at RIT, and he's talking today. The title is a little changed now. Is cavity optomechanical sensing and manipulation of an atomic persistent current. So, Mishkat.
Thank you very much, Anand, for your kind introduction. So, like he said, I actually am a regular visitor in normal years to IIT Kanpur. If you don't believe me, you can go to his QuiC Talk website and you can see my previous talks listed there. And I also have been associated with Professor Vanre and Saikat and Professor Ghosh, and many others. So it's really an exciting time of the year for me to come and visit IIT Kanpur. And this year there is extra excitement because there is apparently a leopard on campus. So I will speak on this topic, and actually the original announced topic is a subset of this work, and I'll briefly refer to it. But as Anand said, the idea is to sort of have a tutorial and a discussion, and not really trying to impress the two experts in the audience with all the latest and greatest technical advances. So I hope to carry at least 95% of the audience with me right till the end. So this is going to be a basic level talk. And actually I think the work itself is also pretty simple in principle. So this is our recent work, and of course Anand is a collaborator on this work. And this is just a quick overview of our quantum optics theory group at the Rochester Institute of Technology, which you can see in the high and low temperature regimes here. We are mostly focused on light matter interactions, and there's a sampling of the topics we are working on with a number of collaborators. And I've highlighted I have lots of collaborations in India, and I'm always looking for more. I would like to at least double, if not triple, this list. So if I have not already approached you, please feel free to come up and we can discuss. And I would love to learn what you're doing and maybe even do something together. Perhaps as importantly, the institution I'm at, the physics department, does not have a PhD program. So I have no graduate students. I work mostly with postdocs, and a good number of them come from India. So Pradeep, who is the lead author on the topic I will discuss today, came to me from IIT Ropar. He's a Shubhrangshu's student. Sandeep came from Taraknath Dey's group at IIT Guwahati. Kani from Professor Harsha Vanare's group here. Arpita came to me from Professor Bimalendu Dev's group at Cultivation, and so on. So I'm actually currently looking to hire anywhere between 1 to 3 postdocs. So if you're interested, please contact me. And the topic will be essentially what I'm going to discuss today. So here's a brief outline of my talk. I will first introduce atomic superfluid rotation. Then I will introduce cavity optomechanics. These are two very substantial but quite distinct areas at the forefront of contemporary physics research, in my opinion. And our work is to try and combine them in a fruitful fashion. And the specific problem we are going to try and solve is using cavity optomechanics to sense the rotation of this atomic superfluid. But by the time I finish, I hope to convince you that this is just the tip of the iceberg. There is a number of interesting questions in atomic superfluidity for which cavity optomechanics provides us a very versatile and long-ranging toolbox. So we can solve a lot of the problems in this field. Just to remind you, the first kind of superfluidity to be detected was superconductivity, which can be thought of as a kind of charged superfluidity. So this was Camerlingone's discovery in 1911. And those observations, as well as the ones that followed, were described very famously by Bardeen, Cooper, and Schrieffer, who gave the theory of superconductivity, and they were recognized with the Nobel Prize. But in 1986, and since then, a number of superconductors have been discovered experimentally which do not follow the BCS theory, and they are not described by any known theory. So the theory of high temperature superconductivity is one of the biggest open questions in all of physics today, I would say. In the meantime, superfluidity was discovered in liquid helium, and first in the bosonic and then in the fermionic isotopes. In this talk, I will actually focus on atomic gaseous Bose-Einstein condensates, which were experimentally achieved in 1995, because they offer a really flexible experimental platform which allows for all kinds of control. You can change the species, you can have spinor condensates, you can have spin-orbit coupling, you can put fermions in there, you can have dipolar degrees of freedom, long-range, short-range interactions which are tunable, etc., etc. And also rather simple theory, microscopic Hamiltonians can be used to model the physics. So it's very attractive from that point of view. But I should say that there are many, many other systems in which superfluidity has been either found or conjectured. So for the purpose of this talk, Bose-Einstein condensation will be considered to be a manifestation of the wave nature of matter. At room temperatures, we know that the atoms in this hall, in this auditorium, can be modeled pretty well as billiard balls. But if we keep lowering the temperature, then the de Broglie wavelength associated with every atom increases and eventually becomes comparable to the interparticle spacing. And that's said to be the critical temperature for Bose-Einstein condensation. Far below that temperature, every atom corresponds to a wave, and all these atoms and waves are indistinguishable from each other. And they are all in step, so there is some kind of collective behavior for which the technical term is coherence. Okay, so this is a coherent matter wave. In his original proposal, Einstein, when he proposed BEC with material particles, did not consider interacting particles. He considered non-interacting particles. But in my talk, following experiments, I will assume that the atoms repel each other very weakly. I would like to go over how atoms in a condensate interact with various kinds of electromagnetic fields in this slide, because it's going to be useful throughout the talk. So it's a quick run through. I'm sure you know all this already, but just to remind you. The transition temperatures for Bose-Einstein condensation in atoms is very low, hundreds of nanokelvin. So we cannot store these condensates in any kind of material vessels because we don't know how to cool matter, bulk matter, to those temperatures. So really they are contained in traps made of electromagnetic fields, and a very popular one is a magnetic field. And the most popular kind of magnetic field trap is the harmonic trap. But we are not going to focus on that. In this talk, I will be more concerned with the ring or toroidal magnetic trap. And this kind of trap is said to be simply connected. This is said to be multiply connected. Basically, that refers to how you can continuously deform a path between 2 points continuously into any other path. Atoms in the condensate can interact with laser light. If the laser light supplies photons which are resonant with some transition in the atom and satisfy the selection rules, then the atoms get excited out of the ground state, go to some excited state, and eventually, due to spontaneous emission, come back down. And what this spontaneous emission process does is that it emits a photon in a random direction. So there is a momentum recoil that the atom experiences also in a random direction, and this randomness of the recoil destroys the coherence of the condensate. Actually, you don't have BEC any longer. And the reason I'm mentioning this is that one of the important points of this talk is that to measure or observe anything about these condensates, essentially you have to carry out some form of what's called absorption imaging. You shine light on the atoms, which is close to resonance, and you look for a shadow on a screen, and that destroys the condensate. What if the light is off resonance, so far off resonance that the probability of the atom occupying the excited state is practically zero during the experiment? In that case, you can ignore the excited state. Something interesting still happens to the ground state. It undergoes an energy shift. It's often called the AC Stark shift. So here I'm showing the shift for an atom moving from right to left across a focused Gaussian beam. So you see the shift increases until the atom reaches the axis of the beam where the intensity is the highest and then goes back down. So what this says to me is that if you have such a focused beam, you can use it to push a sufficiently cold atom around. And actually, that's the configuration we will refer to. So here we have a Bose-Einstein condensate of atoms confined to a ring, and now we have a focused atom beam represented by this plane, which is now used to push or stir these atoms. And you find if you do that, you can set the atoms into a state of flow. Now, if you look at the angular momentum per atom divided by h bar, this quantity, which is sometimes called the winding number of the condensate and sometimes the topological charge, then you find that takes discrete values as a function of the frequency of the stirring. Okay, so if you don't stir, none of the atoms are moving. Then you stir a little bit, nothing happens until you reach a sort of critical frequency of stirring, and then all the atoms start moving with h bar worth of angular momentum. And then if you stir harder, you go to 2h bar and so on and so forth. So quantized rotation is actually a hallmark signature of superfluidity. And the first experiments which demonstrated currents in this geometry were carried out in the group of Bill Phillips, who you might remember was awarded the Nobel Prize for laser cooling and trapping. So this system can be described in some simplistic sense by a wave function, sometimes called an order parameter, which is quite easy to write down. So here we have n, which is the linear density of atoms on the ring, divided by 2 pi. There's a square root, so that's kind of the amplitude. And then there's the space factor, which contains the winding number or topological charge. So LP equal to 0, no rotation. LP equal to +1, rotation along a certain direction, depending on your convention. And then LP equal to -1 is same magnitude of rotation, but in the opposite direction, and so on and so forth. So now, why are we interested in this topology? Let's consider LP equal to 1, so a charge 1 vortex, but not in a ring condensate. Let's just consider in a harmonically trapped condensate. And you can follow that vortex by looking at this black dot, which is the core of that vortex, and you can see that it's actually moving around. Actually, it's precessing around the center of the condensate. What the ring trap does is that it stops this motion. It pins the vortex down by enforcing a density null everywhere except on the ring. So at the center and around, the potential is stiffen up, too steep for the atoms to go there. So the circulation is confined and localized to this ring, which is useful if you are trying to examine the vortex or manipulate it. Now let's consider LP equal to 2. So a doubly charged vortex, again, in a simply connected Bose-Einstein condensate. You can see that eventually that dissociates into 2 charge 1 vortices. And that's simply because the energy of this configuration is lower than the energy of this configuration. The energy goes as the square of the angular momentum. So you can figure out that h bar plus h bar, h bar squared plus h bar squared is 2h bar squared here. And here it's the square of 2h bar, which is 4h bar squared. So that gives the higher energy. The ring trap, again, prevents this kind of dissociation. If the ring is steep enough, you can actually set into motion and sustain states of very high circulation. So there have been 2 experimental papers recently which have gone up to 40,000 h bar worth of circulation. This is moving at 15 times the speed of sound. So the paper is called Hypersonic Bose-Einstein Condensates. This is the experiment of von Klitzing. He's in Crete. And then I think this one is a French group from the Sorbonne who achieved 350 h bar per atom. So very high states of circulation can be maintained in this ring topology. Lastly, I should mention that these states of flow persist for a long, long time. Okay, so the non-rotating state is the ground state. Any other state with non-zero angular momentum is actually an excited state. So it's not going to be infinitely stable, but these states are metastable. In fact, they persist for minutes. And anybody who is interested in coherence, either in the fundamental sense or in the sense of trying to make a device which exploits quantum coherence, I think needs to sit up and take notice. I don't think there is any quantum system which shows that much, ions or NV centers or superconducting circuits or mechanical resonators. None of them has such a long coherence time. And actually, this is just limited by vacuum. So if you have a really fancy vacuum system, I think you can really even improve on this. So it's a really remarkable system. So those are the things that attract. Yes.
So this argument you gave, the energy argument for breaking up the thing center to two, the orbits. So, but there should be some sort of if these are such isolated systems, there should be some angular momentum argument also which force these things to be these two ones to have different projections or something.
Sorry, what's the question? So there, go ahead.
This
So angular momentum here is 2h bar, it's 2h bar here also. Angular momentum remains the same.
angular momentum.
Yes. Yes. So it's the balance between the mean field repulsion and the kinetic energy due to rotation that decides what the global minimum is.
And this, what sets this minutes kind of?
This is just the background collisions of gas.
Is that angular momentum sensitive, this time scale?
So far, no. They have looked at currents up to 15 h bar, actually up to 40,000 h bar.
Similar times.
It's pretty much limited by the trap lifetime. Yes. So from everything I've said here, I hope it will not be a surprise if I claim that these rings are actually paradigms of quantum rotation. They offer us a localized object which we can set into a state of very high rotation and which persists for a long time. Okay. So it's not a surprise.
Mishkat,
Yes.
how do you measure this, the NP value?
Aha, that's the central point of this talk. I will talk about it in great detail.
Sorry. Okay, yeah, go ahead. Don't bother.
Very good question. So, yes.
What do you mean by unstable? It breaks into smaller pieces? What do you mean metastability? Metastability, 0.3.
Metastability, it just comes to a stop.
Or stop.
Yeah, I mean, you lose atoms from the trap is what happens.
LP becomes 0 or?
I should be more careful. You lose atoms from the trap. You start with 10 to the 4 atoms, you wait for a minute, you'll go down to 10.
I see. So there's a transfer of angular momentum also to
To the background. Yes. So a lot of people are interested in these systems. Of course, it's a very nice system to study superfluid hydrodynamics in. Shock waves, phase slips, various kinds of collective excitations, some of which are shown here. It's also a very nice geometry for matter wave interferometry. If you can inject atoms, then you have these two arms, and then there's a recombination at the end, and you can look at the output. And actually, people are actively looking at making devices which are analogs of Josephson junction elements in solid state physics, and you do that by having a tunneling junction here. So this is again just a laser beam which is focused, but now it's semi-permeable. Okay, so atoms can tunnel through it, and these tunneling junctions allow condensates which are circulating to sense rotation, just like in Josephson junctions. They can sense magnetic field. You can do all kinds of other things, examine sort of Kibble-Zurek theories of topological defect formation, model early universes. I want to focus a little bit on some recent news over the last 1 year, which has been very exciting. So 2 groups, one in Dartmouth and one in Florence, have put fermions on these rings. And they are able to tune via a Feshbach resonance, for those who know, basically an external magnetic field. They can tune the system from the so-called BCS to the BEC limit. And what that means is that they see superflow from here to here. In this so-called BCS limit, the flow is due to fermionic pairs. And the bonding length of these fermionic pairs is much larger than the interparticle distance. This is actually the scenario that applies in a conventional superconductor, the Bardeen-Cooper-Schrieffer superconductor. At the other limit, the fermionic atoms are tightly bound into bosonic molecules. That forms a Bose-Einstein condensate, so it shows superfluid behavior. Now, in the intermediate case, actually, is a lot of focus because the coherence length of the fermionic pairs is comparable to the interparticle spacing, and that actually is what happens in some of the high temperature superconductors like the cuprates. Actually, there are connections to quark, gluon, plasma, and bilayer graphene also, but those are way outside my expertise, so I won't say too much about that. But there's a lot of interest in looking at these systems. And one of the sort of bottlenecks is the fact that nobody has seen fermionic superflow directly in these two regimes because the superfluid fraction is low. When you do expansion techniques, the Cooper pairs break up, etc. So always a quick sweep of the magnetic field is used to project back to the condensate limit, and then you can establish the flow of persistent currents. But you have to make assumptions about the dynamics. And I'll say why I'm pointing that out in a second. So as Professor Wanere said, you can imagine that in all of these experiments, a very important question is, what is the state of rotation of the condensate?
One quick question.
Yes.
In the previous experiments you were showing, are these charged superfluids or neutral?
These are neutral. So there are a number of techniques for measuring BEC rotation. There are about 5 or 6 to my knowledge. I'll mention a few of them, and then I'll say what's common to them, and that's the bottleneck we're trying to conquer. So if you have, like I showed you, a vortex, there is a dark core from which the atomic density is expelled. But if it was just a hole, and you switched your trap off and you allowed the atoms to ballistically expand, they would expand in every direction. Basically, they would fill up the hole. But if you have angular momentum due to the centrifugal force, the atoms would still be excluded from the center. In fact, the faster the atoms are going, the larger would be the core size of the vortex. So one of the ways of measuring LP is to just switch off your trap and wait. And if you have no charge, you will still see a blob. If you have a charge 1 originally, you will see a small core and so on. And the core size actually is a function of the orbital angular momentum. I forget if it goes linearly or the square root of orbital angular momentum. But from here, you can reliably extrapolate back and say, okay, I had a charge 11 vortex. That's one way of detecting. And what it does is it gives you the magnitude of the rotation, but not the direction. There is a very nice technique of obtaining the direction as well as the magnitude, and for that you have to set up this so-called target potential. Okay, so the ring is what you're interested in, and this central Bose-Einstein condensate is a disk which is not rotating. You switch off your traps, the ring and the disk interfere. If the ring was not moving, the disk is not moving, then you get fringes due to matter wave interference which are concentric. If the ring was moving with charge 1 along a certain direction, you get a spiral with the appropriate handedness. If it was moving with charge 1 in the opposite direction, you get a spiral with the opposite handedness. If it was moving with charge 2, you get 2 nested spirals with the right-handedness. Okay, so it's very beautiful. There are more complicated techniques where you can play games with the internal structure of the atoms so that the final image you take has a number of lobes exactly equal to the charge of the original vortex. Okay, this is the work of Zoran Hadzibabic at Cambridge. What I want to point out, and there are many more methods, what I want to point out, however, is that in every case, no matter which technique you choose, in the end, you have to take a photograph. You have to do this absorption imaging, which destroys the condensate. Okay, so you have to continuously refresh and prepare fresh condensate. Aisha, did that answer?
40,000 H bar, you won't get a shift, is it? I mean, if you measure sort of a Doppler.
You're getting there. You're getting there. No, that's kind of the idea. So we're
also for this one, measuring the radius to guess or determine the charge. This will work only if you have one single value of m. If it's
a superposition, yes. That's right.
Superposition, it won't work.
No.
So people have, people have put in the superposition.
No. I was going to say that, but I waited for the question. Yeah, so they have created a superposition in simply connected BECs. This is Bill Phillips' experiment. He has created a counter-rotating superposition of plus H bar and minus H bar, but that's an harmonic trap. Okay, so you get the usual, the Chinese ideogram.
It's a structure in the phi direction.
Yes, exactly.
And again, sorry.
Yeah, no, please.
The rotation is always through a beam that is pushing it around.
So
why not Anand's beams?
very good question. So I did not address how these things are prepared. There are actually multiple methods of preparing them also. So like I said, initially you can stir. That's optical stirring. You can just take your magnetic trap and do this, like you stir your lassi or your coffee. Okay, and that's what von Klitzing does for his 40,000 H bar. you can use the internal structure of the atoms and carry out these Raman transitions, which take you from non-rotating states to rotating states. Here is something more interesting, or maybe as interesting. You can set up barriers around the ring before you make a condensate, and then you make these 10 condensates. Each one of them forms with a different global phase. Then you lower the barriers, so there is a phase gradient between neighbors, and that starts rotation. You can't predict what that rotation is. Actually obeys the Cable-Zurek law. Overall there is some scaling, but at random you will get some rotation, a pure rotational state. So those are some of the techniques, but there are others also.
So is it rotation of the phase front, or is it the actual matter rotation?
It's actual matter rotation. There's angular momentum per atom being transmitted. Okay, so I hope everybody in this hall will agree with me if I claim that ideally a measurement should be non-destructive, it should be carried out in situ, and it should be carried out in real time. Yes? So if we look at the history of superconductivity and superfluidity, actually an enormous amount of effort has been put in to implement measurements like these because the vortex dynamics in these systems is very rich. And as a result of the success of these techniques, we have learned a lot about such dynamics. A similar campaign has been started in the case of simply connected BECs, but these are very challenging experiments. Okay, progress has been relatively slow. So what we are asking now is that we have these rings that are available to us, and is there any way in which we can carry out this kind of a measurement in this ring system?
So from very maybe naive perspective, the quantum measurements are usually destructive.
Yes.
Especially the strong measurements.
Yes.
So how can you have completely non-destructive?
So one answer is that there is this class of measurement called quantum non-demolition measurements. There is a number of criteria which you have to satisfy, one of which is the variable you're trying to measure has to be a constant of motion of the system, etc., etc. The measurement Hamiltonian has to commute with everything. But there is another class of measurements which are dispersive and weak. So they're not projective. And if you carry them out enough times, then you can carry out a minimally destructive measurement, in which class our proposal lies.
So these are kind of like probabilistic, that even in the non-demolition, you are increasing the probability of detection, but it's never happened.
No. Yes, it's a deterministic, because it's a dispersive measurement. That means you're not projecting, this is...
What happened to the eigenstate thing? Only if it's an eigenstate, then you know it for sure. If it's anything else, then you're never sure. So that basic quantum thing.
That's what we will address. We will address the case where the condensate is actually in a rotational eigenstate, and we will show how to measure that, and I will quantify for you the back action that results from that measurement. Okay, I will give you the full noise budget of how much disturbance is involved. Okay, that's very nice, very deep question actually. Okay, so there are actually experimentalists have already declared that that's kind of a desirable aim. This is from Bill Phillips' group about a few years back. But again, this paper uses projective measurements and destructive measurements. So this is a sort of a grand aim, and so we thought, okay, some new kind of thinking, some injection of idea from another area is required for achieving this. And we looked around, and then we decided we should take the help of one of the most amazing sensing paradigms available in all of physics today, and that is cavity optomechanics. Now, cavity optomechanics, the best known example of this technique is LIGO, Laser Interferometer Gravitational Wave Observatory, which reported the observation of gravitational waves predicted by Einstein's theory of general relativity and was recognized with a Nobel Prize. So here is a schematic of LIGO. For the optical physicists here, they know this is a Michelson interferometer, but these are basically just an optical arrangement, which I will describe. So here's a laser. It's sending light in, which is why we have opto in the title. And then light is bouncing back and forth between these mirrors, which form cavities, which is where this comes from. But the mirrors are actually not pinned down. They're oscillating like pendula. They're suspended from some support, and that's where the mechanics comes in. And the idea is that when the gravitational wave passes by, it interacts with these mirrors, and causes a relative path difference between these two arms. So when the light comes back out and is seen by this photodiode, it is modulated by the passage of this gravitational wave. Okay, so you can see one of those traces here. This is a real-time signal taken over about half a second. And according to Einstein's theory, this is due to a gravitational wave which was released when two inspiraling black holes many, many years ago merged. Now, if you convert this amplitude into the displacement measurement that LIGO carries out of the path difference, and you can do that by multiplying, the amplitude is actually called the strain, by the length of the interferometer arm, you find it's a very, very small number. It's a fantastically small number. Okay, 10 to the minus 18 meters is a 1,000th of the radius of a proton. So what this is saying is this paradigm of measuring motion by transducing it out with optical fields is very sensitive. It's very powerful. Now, to be sure, LIGO is a very fantastically complicated device. Each arm is 4 kilometers long. But you can take the same physics and reduce it to tabletop experiments and still make very cutting-edge sensors. People have made accelerometers, devices for measuring magnetic fields, electric fields, temperature, any physical variable that you can couple to the displacement of your oscillator. Is that me? Yeah, sorry. That you can measure with very good sensitivity. So the basic physics of cavity optomechanics can be understood using a much simpler layout than the one I just showed you. So here we have just two mirrors. One is fixed, and the other is harmonically oscillating along the cavity axis, and this is driven by a laser. So the person who first gave a sort of rigorous and well-derived theory was C.K. Law, who was actually a postdoc when I joined the University of Rochester in 1995. I used to see him walking around the corridors late at night, and I used to think, what is this guy doing? So this is what he was doing. So he wrote this cavity optomechanical system in terms of two oscillators. So now I'm using second quantized notation. So the first oscillator is this optical cavity mode that the laser excites. Okay, so A dagger creates photons and A destroys photons. The second oscillator is the mechanical oscillator. So B dagger creates phonons and B destroys phonons. And he described the interaction of these two operators, which can be understood simply in terms of a force. So you can see the linear momentum carried by a photon when it's reflected by the end mirror is completely reversed. So there's a change of momentum. And this happens every time the photon comes back and recirculates. So there's a rate of change of momentum with respect to time. And so that's a force. And it won't surprise you to know that the force is basically due to the radiation inside the cavity and is proportional to the intensity or the number. So in the interaction term, you have the number operator. And then this force couples to the displacement of this end mirror. Okay? So sometimes I like to refer to this as the law interaction. This was known before Law, but this is sort of, he gave a he wrote the Lagrangian for the system, and it's a very highly cited paper, actually, it's thousands of citations. So people have been looking at this interaction for about 4 or 5 decades now, and cavity mechanics, optomechanics is a very mature field, and actually you can do a lot of things with this coupling. So this is what allows LIGO to make the very fantastic detections that we've just talked about. You can go below the quantum limit of mechanical motion. You can detect the back action that your measurement is causing on the system. You can actually devise a scheme for evading that back action. You can squeeze the mechanical motion. You can cool it down to its ground state. You can store and retrieve optical information from it. You can make it look like a laser. You can create entanglement. I'm actually running out of space on this slide. There's a lot of applications. It's really a toolbox for measuring and manipulating mechanical motion. So our motivation was, can we use a cavity in some way to couple to our ring BEC and yield this kind of law interaction? And if we are successful in doing that, then we can use this toolbox to solve many interesting problems. So one thing I want to say is that it is possible to go beyond the law interaction. And that's basically set by the fact that the cavity, by recirculating the photons, supplies feedback to the mechanical motion. So if you take the mirrors away, you take away that passive feedback, but you can put some detectors in place and create active feedback. Okay, you might measure, for example, the particle displacement and then use whatever transfer function you like and modulate the trapping beam for the mechanical oscillator and then engineer the light matter interaction. This has actually been a line of investigation we followed with our collaborator Nick Vamivakis for quite some time. I won't say more about it in this talk, so let me go back. How to couple the BEC to the cavity. There is a lot of precedent for linear motion of the condensate. The first pioneering experiment, this actually was one of our main inspirations, came from Tilman Esslinger's group in ETH in Switzerland. And he put a harmonically trapped, a simply connected BEC inside a cavity and coupled it to the fundamental optical mode, which formed a standing wave. And the BEC coupled to this light wave, I will describe that in detail, in such a way that you could look at the cavity transmission and get information about the motion of the condensate. So really what we have to do is to propose the rotational analog of this system. Okay, we take out the harmonically trapped BEC, we put in a ring BEC, and then the question is what kind of optical mode will allow you to achieve the law interaction, and I think you know the answer already. These are these famous beams with orbital angular momentum that Anand and Harsha and many people here work with. So these are beams which go beyond the textbook plane waves, which have plane wave fronts, and are said to be chargeless, and they have no topological charge. And then you have the charge plus and minus fields that carry angular momentum in their phase profile. Anand, please correct me if I'm saying anything wrong, as opposed to in the photon polarization. And if you look at, for example, the transverse intensity profile of the L equal to +2 or -2, you will see basically a ring. This is where the light intensity is maximum. There's darkness at the center and outside. So this already gives a hint about how to couple to the ring BEC. But now if I interfere the +2 and the -2, I get 4 maxima sitting on a ring, basically an angular lattice. And that's what we are going to use to couple to the Bose-Einstein condensate. So here's our measurement scheme. Here we have Fabry-Perot cavity, 2 mirrors, both of which are fixed. Then we put a Bose-Einstein condensate inside in a magnetic trap, and we assume that it's in a state of rotation. Well, it's in a rotational eigenstate described by this winding number LP, because there are so many ways of doing that. We don't describe how it's done. We just assume it's done. And our task is to measure LP. Okay. So now you can see that if you want to optically probe this system, if you put in a Gaussian beam, that's not going to help, because that doesn't break the rotational invariance of the system, right? If you rotate the condensate as it's moving, it doesn't make any difference to what the Gaussian beam sees. It sees the same thing. But if you break the rotational symmetry by having this kind of interference pattern, then the atom might see a different part of the intensity profile in various different angular positions. Anand? Okay? Yeah. Okay, all right. So we start with the trap ring BEC. BEC has a winding number. Now we drive the cavity with beams carrying orbital angular momentum plus minus L h bar in general, but for our example, I will take L equal to 2. Now, these beams are tuned close to the cavity resonance, but very far away from any atomic transitions. That means the probability the atoms in the BEC will leave the ground state is essentially 0 throughout the experiment. However, as the atoms move around, they are going to have their ground state energies stark shifted as they come around these maxima. Okay? They're going to climb and go down these hills. So if we take a step back, you see what's happening here is that there's a wave going around and encountering a periodic structure. But we know what happens when waves encounter periodic structures. Diffraction. Okay, the more familiar example is when you have a wave which is electromagnetic, usually comes out of a laser, then it encounters a material grating, there is a central undiffracted order, then there is first order diffraction to both sides, second order, and so on and so forth. So here, the roles of light and matter are exchanged. Here, the wave is material, and the grating is electromagnetic, but the physics is the same. So the undiffracted matter wave order corresponds to the original persistent current. And the first order diffraction now consists of 2 more persistent currents, one of which is moving with slightly more orbital angular momentum per atom, and the other with slightly less. Okay? So this is just Bragg diffraction to first order. And of course, these three waves now interfere with each other. And their interference modulates the BEC density, and the photons going through feel that modulation. Another way to think about it is the photons acquire a rotational Doppler shift because of the circulating atoms in their path. Okay? So I will show you that the cavity transmission actually carries the information about the angular momentum per atom of the condensate in terms of these side modes.
So,
Yeah?
so here basically you have to have a specific periodicity to have that plus minus 12.
I'm sorry, need to have a specific periodicity for?
Periodicity of that rating, angular rating. Not all periodicity will give you this plus 12 minus 12, right? Or
Sure. Yeah, so this in general, it's if you have, we explore different L, so it's just different number of antinodes. The number of maxima will change, and actually that has some interesting effects, but you will get this.
what sets the splitting?
I'm sorry,
What sets the splitting of the...
these two? I will explain that. So right now I'm just showing you an angular momentum splitting, but really we should think about energy or frequency, right? Yeah.
So this is the cavity output spectrum.
This is the cavity output spectrum, which I will describe how it's.
Mishkat,
Yes, please.
Just say you had only one of the ends,
One of
plus
the.
minus. I mean, you don't have the light shift kind of interaction.
So if you just have one of the L's, I believe the azimuthal profile inside the will be uniform.
No, but there will be a phase jump which should traverse. Right? I mean, that's what is giving the spirality.
There will
When
be
you come back,
there will be a
you don't
gradient.
come back, right?
There will be a gradient in the phase.
There will be a gradient in the phase.
There will be a gradient in.
And won't that be even weaker measurement than what you do?
That will be a weaker measurement. Actually, I'm not sure what the coupling of that to the atoms will be.
I mean, that's whether we can really transform this to a.
Yeah. So we have to think about that. Yeah, there will be a phase gradient, which probably will be seen by
For
the.
example, okay, we can talk about if you have a sort of a dark state kind of a preparation,
Mhm.
then it's a superposition between the ground states.
Mhm.
It's very phase sensitive.
I see.
So if you,
But are they eigenmodes of the cavity?
no, this is for the light.
That's what I'm saying. So here, you'll see later, I can build a simple analytical model because the modes I'm choosing to probe the condensate are eigenmodes of the optical cavity. If I choose different, I could have just put one step here and not these three, just a notch. It's possible. But it's not an eigenmode of the cavity. It has an expansion in terms of infinite number of eigenmodes, so the dynamics becomes very complicated. So I have chosen some symmetry adapted modes, which the cavity supports, actually just one mode, if I take the superposition of these two as one mode, and that allows me to do that. I'm sure there are variations that you can think of that are cleverer and more. So this is, like I said, this is sort of very tutorial level, basic first knee-jerk reaction to the problem, and now we are looking at the details of this, which are interesting. Okay, so here's our mathematical model for the system. How are we doing for time? Do you know? Okay.
15 minutes.
15 minutes. Okay, I have to push a little bit faster. So this is a one-dimensional Hamiltonian because that's the simplest one. It's a minimal Hamiltonian, okay? The reason you see an integral here is because it's a many-body Hamiltonian. We are trying to sum over all the atoms, but each atom is spread out around the ring, so we have to integrate over the angular variable. This is the rotational kinetic energy of the atoms around the center of the cavity. I is the moment of inertia of the atom around this point. This is the interaction with the optical lattice. The e to the IL phi and e to the minus IL phi give you a cosine IL phi, and the intensity goes as cosine square. So I don't know how the phase would couple to this. Okay, but anyway, this term accounts for binary collisions in the Bose-Einstein condensate. Like I said, I assume these atoms are weakly repulsive. This term is the electromagnetic energy of the mode, and this is the driving term. I'm writing everything in the frame of the frequency of the driving laser. So going back to the physics that I explained earlier, I will now make a guess for the atomic wave function in terms of the original persistent current and these two diffracted side modes. These are all plane waves going around the ring. And LP is the winding number of the original side mode, and LP plus 2L and LP minus 2L. Sorry, of the original persistent current, and plus minus 2L are the side modes. These C operators are just bosonic annihilation operators. So if you normalize the wave function to the number of atoms you started with, then you just have the number of operators for each mode. Now, typically in experiments, we start with about 10 to the 4 atoms. And in our scheme, the lattice is very weak. Actually, there is far less than 1 photon on average inside the cavity. So the number of atoms diffracted into these side modes is very small. Okay? So we expect that the dynamics of the original persistent current is not going to be influenced very much by quantum fluctuations. They're going to be essentially classical dynamics. So we are going to assume that Cp is a complex number. It's not an operator. This is the mean field approximation. And then the truly quantum modes are these 2 modes, which are not occupied highly. Throwing all this together, we come up with a Hamiltonian which looks pretty much like the one that has the law interaction. Instead of 1 mechanical oscillator, we have 2 because of these 2 side modes. But the coupling is exactly of the law form. You have the displacement coupling to the light intensity or number. And then there is an extra piece because of the collisions in the condensate. So I will first give you a hand-waving argument which neglects this piece and tries to establish the physics, but in the final results I will include them. Now the important thing is that the mechanical frequency of oscillation of these bosonic modes contains the parameter we are interested in. This is the frequency, or these are the frequencies that we expect to see in the cavity transmission and that allow us to recover LP. So ignoring the collisions, we have our Hamiltonian. We can write the equations of motion. Now we've included some damping and some noise. This is allowed to me by the, this is made possible by the quantum Langevin equation approach. So this basically tells me that the persistent current doesn't last forever.
Just one slide back. So since n is pretty large, and we want to find the LP about that condensate,
yes.
That is essentially a classical system. So that non-destructive part for the quantum aspect doesn't apply there. I mean, here one can actually have non-destructive because this is a macroscopic system.
Well, the measurement we are carrying out is actually on the quantum modes.
Photons will be destroyed. But
no.
VC you're not destroying.
No, neither photons nor VC. So this is a dispersive measurement which is far off resonance. So you recover all the, there's no absorption and emission, you recover all the photons. It's a very weak measurement, and what the cavity does is it allows you to do it many times before the photon leaves. Okay, so
even if you assume that your number of atoms occupying the condensate is not too many.
No, we're saying it's too many.
You are saying at the moment it is too many.
Oh, if you are saying, even if they're
not too many.
Yes.
The scheme should work.
The scheme should work. You will probably have more noise, and you have to account for other fluctuations.
Because it's not as though one atom is carrying h bar.
That's correct.
It's the collective collective wave function that has that.
Both.
No, your moment of inertia is mr squared versus
Single atom.
Single atom.
So your splittings are independent of n.
The splittings are independent of n.
So it doesn't matter whether you have a 1 atom which is going into this phase or you have a BEC.
It would be a more
cavity splitting, you expect it to go as square root of n.
You might get some corrections to it if you take the quantization of the original persistent current into account. In this approximation, it comes out cleanly.
I mean, see, for example, to get the number of cooled atoms, that's a non-trivial problem.
That's correct.
But you have the I there that will tell you a lot more about the number.
No, so I is single atom moment of inertia, as Saikat pointed out. This is the moment of inertia of a single atom of mass m around the center.
Is this a single, collective mode, right?
It is a collective mode.
Psi is your condensate wave function, no psi phi.
Yes. So since each, so this is a single particle Hamiltonian, and the way you write is to sum.
The curvature of the derivative, like the.
And the way you write the many body Hamiltonian is to sum over all the single particle Hamiltonians. So that's why you have this piece, and then averaging and integrating basically gives you the collective effect of all these atoms. Okay.
So the Hamiltonian is for the excitation over the condensate, right?
That's right. These are both excitations over the.
One particle is coming. One particle I is coming. For omega CD.
See,
It's a ground state.
No, these are both excitations. I'll have to think more about why the single particle.
Mishkat,
Oh, wait, I think I have the answer. So the number of excitations is actually counted by these operators.
correct.
Yes.
Okay, so this is just the shift per excitation.
Okay.
Yes, that's
why
correct.
it's
That's correct. That's correct.
excitation mass.
That's correct. That's correct. That's correct. There is so much interest in this talk, I think I'll have to go a little bit over time. Is it okay?
Yeah.
Sorry, Harsha, you were saying
We'll
something?
make you give more talks. No, see okay, anyway, we'll settle it.
Okay. So now let me just do a hand-waving argument, a heuristic argument, by neglecting the damping because the persistent currents last for a long time, by neglecting noise because the BEC, although it's not at zero temperature, it's pretty low, it's 10 nanokelvins. And let me neglect also the driving due to the radiation force because I said the number of photons is very low inside the cavity. Okay, so I'm neglecting everything except the first and the third term on the left-hand side. Everything else is set to zero. So obviously this is just a harmonic oscillator oscillating at frequency omega c. Same with the other side mode. And if I put those time dependencies in here, I see immediately that the field inside the cavity is modulated at frequencies omega c and omega d, which means my transmission should have those two peaks. That's basically the idea of the measurement. So now
Your XCHD are normal modes.
XC, yes, they are bosonic excitations on top of the original persistent current. So let me now give you the full numerical analysis. This is a sampling of the parameter. There are many parameters in the system because the atomic superfluid problem brings its own set of parameters and the cavity optomechanics brings its own. But I've tried to highlight the ones that gives you some sense of where these are. So about 10 to the 4 atoms, about a few tens of microns radius for the ring. We treat states of low flow for now. This is not an unreasonable cavity finesse, I think the experimentalists will tell you, and so on and so forth. So this was the original title of the talk, so we just have a follow-up paper with Amarendra that's got reasonable reviews, so we are hoping it will be published in PRA soon. So here are...
I'm curious about the healing length.
Yes. Yeah, so we just made the ring thin enough that it doesn't support vortices within, and all the vortex motion is around the center of the ring, because they happen in experiments which have annuli or disks rather than rings. You can get vortex motion within and that complicates theorists, we can do this. Okay, so now I will come to the full numerical calculation. So here, the continuous curves are the collisionless calculations, and the dot dashed include the atomic interactions in the condensate. So if we look at the steady state by setting all the time derivatives in our equations of motion equal to 0, they turn out to give us a set of nonlinear equations. This is very familiar to those people who know optomechanics like Saikat and Harsha. If you go to large enough input power, you will see bistability in the system. So here is a plot of the photon number inside the cavity as a function of input driving power. For low powers, you get a single solution, and then for high enough powers, there's a threshold, and you get 2 stable and 1 unstable solutions. So this is pretty not a surprise, but what is remarkable about this is that you see this already at the level of very low number of photons, 10 or 15. Actually, the ETH experiment I referred to sees bistability at less than 1 photon on average in the cavity. So this is quite remarkable, and this happens because the coupling between light and atoms is very strong. And typically in optomechanics, one writes what's called the single photon cooperativity, which is the ratio of the coherent coupling between light and matter to the dissipation in the system. And the cold atom systems typically are right on top here. They have 10 to the 4 or so of cooperativity. So what that means in real terms is that all kinds of quantum effects are easier to see in these systems. Okay. Now we look at the fluctuations around this steady state. So we are going to stay away from the bistable region and just go to monostable dynamics. And we are looking at the transmission of the cavity. The right thing to look at is the phase quadrature. And if we look at the fluctuations in that quadrature, of course, what's happening inside and the cavity dynamics can be related via standard relations in quantum optics to what comes out. So if we look at the output noise spectrum as a function of frequency, sure enough, we see the 2 peaks. So the continuous curves are without collisions, and the mean field shifts both peaks. And we have verified that you can actually work backward from the location of either of these 2 peaks and figure out what LP is. Okay, so a nice combination, of course, is to look at the distance between these two peaks, which turns out to be just that. So in an experiment, if you know the moment of inertia and you know the orbital angular momentum, you can basically figure out what LP is. But okay, so here's the noise budget. If you plot the same thing as a function of input power, not frequency, but input power, then you see all the contributions. So of course, the laser that's making the measurement has some noise. So this is your short noise. That's this contribution. If you use higher intensities, the fluctuations with respect to the average photon number go down. So that's one way of decreasing that noise. But as you use higher intensities, you start disturbing your system more. So this is the back action. And that goes the other way. And this corresponds to the fundamental quantum uncertainty in the quantum bosonic mode that we are measuring. And then this little gap is due to the fact that the BEC is not at zero temperature. It's a finite temperature effect. If you put everything together, you get this curve, which is obviously minimum here, and this is called the standard quantum limit, and gives you some optimal power with which to work. So the disturbance to the system is minimal. Okay.
So back action, you mean in simple terms, loss of atoms in your...
No. So
As you keep increasing, you lose number of atoms that do this and they are lost to the system.
Okay, so let me clarify that. In what sense the atoms that interact, that are responsible for the measurement, are lost or not? Okay, so it's right here. So we can calculate the sensitivity and so on. So the first thing we find is the time required for measurement is about 60 milliseconds. So this is far less than the duration of a persistent current. So we claim it's real time. Okay. Now, the number of atoms that are removed, quote unquote, from the condensate into the side modes is actually far less than, so the data I'm giving you is like 0.01 atoms on average out of 10 to the 4 that are removed from the condensate. So you can sort of get a rough idea of how destructive the measurement is in that sense. I should say, however, that we are not switching off the trap. These atoms are not leaving the trap. After all the currents die down, they all are restored to the condensate because of their circulation. Now, if we look at the sensitivities, they're 1,000 times better than, more sensitive than has been demonstrated. So these are sort of the...
Actually, I'm not sure about that. Why should they be restored? What is the source of angular momentum for it to come?
Okay, so they're lost from, they are not lost faster from the trap than the atoms of the original current. They're just like any other atom. They will stay for as long as the original condensate.
What I'm saying is, if I start measuring the current in a quantum manner,
yes,
the current carried by an atom, right? That has changed, no? I mean, you're looking at it as a classical object, that is okay.
No.
I mean, classical in the sense that as a collective, not worrying about the numbers in the trap, right? I mean, the numbers don't...
I'm not sure. So here,
no, it's so, okay.
so we are only looking at the dynamics of these two quantum modes.
But they interact with finite number of atoms, which are lost to the rotation.
Which are lost to the original persistent current.
Yes.
But the average number of such atoms is 0.01 out of 10 to the 4. Because it's a collective excitation, you can't really say one atom has been removed.
Correct.
You know. It's the fraction that carries that current.
So Mishkat?
Yes.
So your lifetime of your measurement time is 60 milliseconds, right?
The time required.
And your spectrums are of the order of hundreds of hertz.
Yes.
Right. So
Times 2 pi.
you're basically integrating your integration time and the signal time oscillations is similar. Right? Do you expect
There is an order of magnitude difference. There is an order of magnitude difference. You can get this fast enough.
than 60 milliseconds?
Yeah.
Because otherwise there will be this BT2 omega response. And
You can stay away from those things. Yeah, that's right. Okay, so you can do go beyond the linear response and look at stability and things like that. The one thing I want to point out is that there is that establishes that there is a sort of regime of linear response. Okay, so here we're looking at the height of either of the two peaks, doesn't matter which one, as a function of driving frequency. So if you drive, there is a regime. If the power is small enough, is large enough to give you a signal beyond the noise, and if it's small enough, then the height of the peaks is independent of the power. Of course, if you put in too much power, the optical lattice will become very deep and start impeding atomic motion. In the end, it will kill the signal. So that's just some common sense stuff. One thing I want to say before I finish. So everything I've said so far is in the nature of a passive measurement. The condensate is rotating, the cavity comes along and makes a measurement. But as I told you, optomechanics is very powerful for manipulating the motion as well. So here's a quick calculation, which we put into the paper, which shows that the radiation actually entangle these two side modes. Okay, so these rotating matter waves, and it's also carried out in the linear response, which gives you the covariance matrix, which you can get logarithmic negativity, and basically looking at Gaussian entanglement. And so if you look at that as a function of the orbital angular momentum of the light, you see that there is a threshold effect. You need some minimum orbital angular momentum, and the way I like to think about this is the light interacts strongly with the atoms at these peaks, and the number of these peaks goes as 2L. So the larger L is, the more often the atoms have this coherent interaction, and then they can beat all the noise and the damping in the system to give you. And this is just a sanity check to show that if you raise the temperature enough, the entanglement vanishes, as in most systems.
So this would be a very controlled way of creating entanglement.
This is a very controlled way of it. Yeah.
What are the two parties here? Bipartite?
And the bipartite are the two side modes created in the excitations on top of the condensate.
Spectrum.
I'm sorry?
In the spectrum,
these two that I showed, these two.
Yeah, but Mishkatul, you see, like, we are also in the same boat in
Yes.
these cases. So regarding justifying this entanglement,
Mhm.
so people might have an argument that, this is not really the useful entanglement because you really cannot spatially separate them out, right? Like you really do not, you have, so for example, this Simon's thing, right, that if you have a classical polarized beam, you take a strong laser and focus it down. The spatial transverse mode and the polarization gets entangled, basically, right? And then the quantum people will say, no, you cannot really separate the polarization of the spatial mode. That's why it's classical. And here it seems like if you just have the cavity as your output detection, there's no way you can separate these two modes non-local. You cannot make them non-local.
So yes, so they have spatial overlap, but they are spectrally distinct in the output. So if you can ask what the entanglement between these two modes are, and people do these kinds of calculations in optomechanics all the time,
true,
right?
But then, then this
So if you're looking at the entanglement as a resource for rotating waves, I think you're right. But if you're looking at the entanglement as something carried in terms of the light field,
use this entanglement for something.
that's right. So I think in this case, actually, it may even just be interesting to look at how this entanglement varies as a function of time, because we have a pretty mesoscopic ring, and you have this object that's delocalized all around it, and this can play into theories of how large size systems decohere and things like that. So this is a very preliminary, it's in the last 1/8 of the paper. And one of the referees didn't want us to put it in there, but we did anyway.
Even for like optomechanics at classical level, when you have this sideband generator, if you look at the cross correlation with them, you will see like highly squeezed.
Exactly.
Right, which is basically like entangled.
Exactly.
Except that the fluctuations are classical.
Exactly. So now I'll finish up. I hope I haven't really too much. So basically, we have theoretically shown that cavity optomechanics can be used to measure ring BEC rotation. I talked to some of the experimental groups. Certainly there are groups which have rings and cavities, Stamper-Kearns at Berkeley, for example. I spoke to Bill Phillips, he was quite interested. I spoke to Zoran, he was. So this is a picture that I often show. This is from Benjamin Lev's lab at Stanford, just to show other experimentalists that very, very complicated configurations have already been, there are 4 BECs in here, there's a DMD or something pumping the cavity mode. This is much more complicated than what we are suggesting. So please take up our theory and do something with it. Okay, now, this rotation business is sort of the tip of the iceberg. What we really have is a coherent and reversible interface between optics and atomic superfluid rotation. So I'll just talk about one possible application that we are actually investigating right now, and that is this atomic memory. So as many people here already are working in, and others know, these photons carrying orbital angular momentum are in great demand for transmitting information, because each photon can carry much more than allowed by the polarization basis. And so people send them down fibers, through atmosphere, even through water. And of course, the information they carry is degraded. And so there is a need for atomic memory or repeaters that you can put at certain lengths along the path. And so far, most of the quantum memories that have been designed for these photons use cold but not degenerate atoms. And the best memory times are like 400 microseconds or so. But it's very tempting to use these circulating currents, which last for minutes. That's a 5 orders of magnitude improvement. And the nice thing is that in optomechanics, people have already demonstrated how to map optical information onto a mechanical motion and retrieve it back out. It's done experimentally. So what we're looking at is how an optical beam with certain OM can be stored and then retrieved from these circulating currents. This is something Pradeep is working on right now. Anyway, thank you very much for your attention.
Very nice. Still have to
answer the question. Lights, less lights.
No, he's the camera.
Camera.
Sorry.
So any questions?
So I'm interested in the gamma. What is the origin of gamma? Sorry, the dissipation. Dissipation term in your Hamiltonian.
So this is a phenomenal. So first of all, dissipation is not well understood in these ring BECs. There are astronomical orders of magnitude difference between theory and experiment in terms of the lifetimes of these persistent currents. That's still going on. There are theories of pure thermal induced phase slips, thermally assisted quantum phase slips, and pure quantum phase slips, and so on and so forth. We just took the numbers from what has been observed in the experiment. How long does a persistent current last? A minute. That determines gamma m. And of course, you have to follow the fluctuation dissipation theorem, but then this accounts essentially for the thermal fraction of the BEC, which is actually not observable in experiments. But we know there is a thermal fraction, some small thermal fraction. And the background gas, which removes, so this dissipation has to cause some fluctuation. So these are the it's a very simplified model of, people write very complicated finite temperature theories for Bose-Einstein condensation, but it's a very poor man's theory.
So, I have a question.
Yes.
In your last slide, you mentioned about this memory storage, right, and readout. What is the time scale you are expecting here from this kind of memory?
So the time scale is basically determined by the duration of the persistent current, which is minutes.
Will it be useful in the measurements, like when you transfer the information in, in the terahertz regime? Will it be useful this kind of?
So we are mainly looking in the optical regime right now. So I don't know. I don't really know about the issues in terahertz physics to answer that. Yeah. This is all theory, by the way.
Second.
Yeah, so suppose you put everything of your entire setup in a black box. And just look at the output spectrum and sending in some LG mode. Right? Seeing these two things. Is there anything like smoking gun signature of a superfluidity in this case? Like for example, I can as well, like you have a VC. I suppose if I stick a faceplate in between and somehow like split up the plus or minus, like actually putting an angular rating. Like how is, like by looking at something on the spectrum, can I say no, this is a superfluid and not a rating, or not an angular rating?
So maybe I can simplify the question by asking, what if we look at the experiment below and above the transition temperature of the Bose condensate, right?
Yeah, so is there a way this goes down? Like,
so the visibility of the interference will change. I'm not sure it will go to 0 at the transition temperature. I mean, matter wave effects have been seen even above BEC transition.
you will see the nature of the phase transition as you
Probably. So
side times, right?
yes. So actually, we are collaborating with Bimalendu Dev, who claims that the bistability in the quantum limit disappears and there's a phase transition. You probably know more about that.
No, so bistability, is it understood in all the branches? What is happening to the fraction that is coupling? I mean, what are they doing?
I don't think.
In terms of
I don't think there has been a detailed.
where one is.
Yeah,
in terms of,
I'm not.
Just accounting. I mean, who has the photon or the extra?
We have not looked at that, and we are not aware of any
It might be
studies.
something worth.
No,
Yeah,
I remember like this Esslingers, like when they were making, of course, 2007.
They have a separate paper on the bistability.
Yeah, but before that, we used to hear him come and talk.
Mhm.
And I think every time a question would be that, suppose you have the BEC fiber in the cavity. By looking at the cavity transmission, can you see the BEC to like ideal gas to BEC transition?
I see.
And I think there is no signature.
I don't think so.
It is a continuous. There is no
I believe that's correct. I believe that's correct.
It basically behaves like an atom.
Yes.
Other question? Okay, so if not, let's do
Thank you very much. Thank you.